So I'm Chandan Dasgupta. I am at our Indian Institute of Science Physics Department and also here part-time. So Partho asked me to give some kind of a tutorial for people who are not experts on stat phys, statistical mechanics. So that's what I'll try to do. There are a few specific subjects in statistical physics that I want to spend some time on because those things have substantial overlap with the other things, machine learning and things like that, that are being discussed in this meeting. So I'll say, first of all, just a brief introduction, then talk about phase transitions in general, because that's one of the things that we'd like to sort of go a little deeper into. As far as phase transitions, as Partho mentioned in the previous lecture, there are some phase transition aspects to it. Then a little bit of technical details about mean field theory, again, something that will come up later in this workshop. Discussions of, again, statistical physics of learning problems. And then I'll just give a brief introduction to disordered systems. Tomorrow there is going to be a sort of more detailed tutorial on using replica methods and similar things to study disordered systems. And so today's, what we're going to do is just introduction to it, and the technical details will be given by our speaker tomorrow. So, and please stop me if there is something that you are not familiar with, because, again, I don't know how much statistical physics you have seen, at least those who are not physicists. So let's just start with the basic idea. I'll be talking mostly about equilibrium statistical mechanics, not so much about time evolution or dynamics. And here, what we are interested in is thermodynamics of the system. Thermodynamics of the system consisting of a very large number of particles. We have already heard about Avogadro's number, so of the order of 10 to the 23rd number of particles. And these particles, or whatever objects those are, they will be interacting among themselves. So it's a question of very large number of particles which influence each other's behavior, and we are interested in the collective properties of such systems. So one is talking about systems consisting of a large number of particles, and typically, theoretically again, often one takes this limit, thermodynamic limit, where we let this n go to infinity, and for example, some things in phase transitions will happen only when this n goes to infinity, not for finite values of n. And generally, to study the system, its macroscopic properties, what one starts with is this microscopic description in terms of some kind of a Hamiltonian of the system, energy function of the system. Tells us about, first of all, what are the different sources of energy, kinetic energy, potential energy, etc., etc. And that one assumes that that is known. And then from that, one tries to deduce certain thermodynamic properties, which are bulk properties of the system when it is in thermodynamic equilibrium. Equilibrium means it's certain external parameters are held fixed, like temperature, pressure, and stuff like that, and the system basically is evolving under those fixed values of those parameters. Of course, it doesn't mean that the microscopic state of the system is remaining the constant. The system is going through a very huge number of different microscopic states when it is macroscopically at equilibrium. So what one wants to understand is some of these macroscopic properties of the system at equilibrium in terms of a specification of some kind of an energy function that tells us about what the basic variables are, and given a particular configuration of these basic variables, one wants to then try to, this tells us about the energy associated with a particular configuration of these basic variables. And here, let's say, I'm not going to, at this point, specify any Hamiltonian or anything like that. Let's say the basic variables, microscopic variables, are this sigma, and these sigmas interact with each other. They can interact with some external source or external field. And this is one of the simpler Hamiltonians, which we'll be discussing as we go along. The objective is actually to, given this specification of the microscopics of the system, use this to get some information about the macroscopic behavior of the system when it is in thermodynamic equilibrium. And without going into too many details, I'll just give you sort of the operational way in which statistical mechanics is used. As I said, when the system is in a thermodynamic state, it is microscopically, it is not in one microscopic configuration of the variables. It is going through a very huge number of different microscopic configurations. So, and this different set of microscopic configurations are represented by what is known as an ensemble. And an ensemble is specified by a set of probabilities. So, I mean, when the system is in equilibrium, it is going through many microscopic states, and we actually don't know. And we are not really interested in knowing what are this specific microscopic states the system is going through. What we're interested in knowing is the probability of the system actually exploring one of these microscopic states during its evolution when it is at equilibrium. And these probabilities are given by this Pn. So n, little n now is going to refer to a microscopic state in the variables that are defined last time, sigma 1 up to sigma n. Specification of a particular microscopic state corresponds to giving values to this sigma 1 up to sigma n. And these values are changing continuously as the system is evolving in time. And what statistical physics, equilibrium statistical physics deals with is basically these probabilities that according to a particular microscopic state n in the ensemble. And if this quantity is known, if this Pn is known for the different microscopic states, then some thermodynamic averages can be calculated with respect to that. So if some observable is whatever it is, energy or magnetization or some such thing like that, this is known, its value is known for a particular microscopic state n, and then you just average over all possible microscopic states with this measure P of n. That is the prescription of equilibrium statistical mechanics. This is what one is supposed to calculate. Okay, so this everybody more or less knows about this, right? The form of this distribution function or density matrix or a probability function, whatever you want to call it, that depends on basically under what conditions you are observing the system. And in particular, we'll be talking about what is known as canonical ensemble, where the probability of occurrence of a particular microstate in the ensemble is given by this quantity. The exponential of minus the energy of that particular state divided by kBt. I am putting this kb equals 1. Kb is the Boltzmann constant. So basically, and this partition function z is normalization condition. It's basically sum over all microscopic states, or exponential of minus energy divided by kBt. So in most of the things that I'll be talking about today, I will use this particular form for the probability function. That the probability of seeing a particular microscopic state in the ensemble is given by exponential of minus the energy of that state divided by thermal energy. kBt is a measure of thermal energy. Given this partition function, one can define various other quantities. Just for the sake of completeness, I'll mention all these things. One is the Helmholtz free energy, which is related to the log of this partition function. And the usefulness of this is that if one has an expression for this, then by taking derivatives of this quantity with respect to appropriate variables, one can calculate various other thermodynamic quantities that are of interest to us. For example, if I want to calculate the energy, internal energy, average energy. So a particular microscopic state n will have energy given by this much. And then this is the probability of system actually being in that particular state. So if you calculate this quantity, that gives you the average energy or internal energy of the thermodynamic state. And this, one can easily see that this can be obtained by taking a derivative of this Helmholtz free energy with respect to inverse temperature. Again, notation, this beta literature always used this symbol to denote 1 over the absolute temperature, T. So this is the framework that is very well known, and most of the studies that people do, theoretical studies of thermodynamic properties of materials, will be following something, if not exactly this, but something that looks like this, more or less. That one has to consider the fact that there are many, many different microscopic states, the system actually explores during its evolution at equilibrium. And there is a probability measure that tells us about what is the probability that the system actually will be in that particular microscopic state. And that probability measure has this kind of a form in a particular ensemble. Okay, so this framework is clear to everybody, right? In the same, just like we are talking about the internal energy here, another quantity that plays a very important role in StatMech and also in the kind of considerations that we'll see this in this workshop is the entropy. And this entropy, there are many different ways. I mean, it's, initially one studies thermodynamics or even statistical physics, there are lots of confusion about what this quantity is and so on and so forth. Here, there are many different ways of defining it, and the way that I am going to define here is sort of like the information entropy, that this P of n is the probability measure of associated with the particular microstate, and you look P log P and sum over all the possibilities. That gives you something which is, and the thermodynamic definition, Clausius definition, Boltzmann definition of entropy, all of them can be eventually reduced to this particular way of defining the entropy. And here again, one can see that this entropy can be obtained by taking a derivative of this free energy with respect to the temperature. So, and here, this quantity is important because, as you'll see, many other things are sort of closely tied to the entropy. And in particular, these are statements that are quite easily seen to be true, that when we make the temperature go to a very large value, then all the microscopic states become almost equally likely. And there, this P of n doesn't depend on n anymore. It just 1 over the total number of microscopic states the system can have, and the entropy is just log of that. And one thing that one should keep in mind is that total number of microscopic states the system can have actually increases very rapidly with n. It's many cases, simple models that we'll be talking about, it's something raised to the power n. So when you take the log, you bring this n in front, so entropy is an extensive variable. The entropy of a thermodynamic system is proportional to the number of particles or number of variables that you have in that system. And the entropy is maximum when the temperature is very large. On the other hand, when temperature goes to 0, then again, it should be clear from this particular form here, temperature goes to 0 is only the smallest value of H will come in there, and those correspond to so-called ground states, the states, microscopic states of the Hamiltonian, for which the energy is the global minimum, has the lowest possible value. And depending on how many such microscopic states are there, one has a degeneracy of this ground states. And if we call that n sub g, then the entropy becomes just a log of that. Now, the point is, this number typically is not a very large number. I mean, if you look at the number of ground states, the global minimum of the Hamiltonian, then generally you have a small number of such microscopic states which globally minimize energy. There are some model systems with disorder and things like that, or with what is known as frustration, which I'll come to towards the end of this lecture. One can have this Ng, which is exponential in the number of particles that you have. And in those cases, you will have basically an entropy, which is proportional to n. But those are very rare. In most of the systems that we'll be interested in, the ground states, there will be a few really truly global minima of the Hamiltonian. And the entropy will basically, entropy per particle will go to 0 at t goes to 0. And this is also one of the things that is supposed to be general. It's the third law of thermodynamics, which under certain circumstances says that the entropy per particle or per variable will go to 0 as the temperature goes to 0. Obviously, these considerations, I mean, how many such global minima are there, etc., those things are related to this optimization problems that were discussed to some extent earlier, that given a function of many, many variables. I mean, we are talking about this Hamiltonian, which is a function of 10 to the 23 variables. Question is, what is the configuration, what are the configurations which will minimize this Hamiltonian? And so this problem is essentially very similar to what we had heard earlier about optimization problems. We also heard about local minima. So I think, just to make, again, a connection between what we are interested in statistical physics of materials and the kind of issues that are going to be discussed in this workshop, I should also mention the importance of microscopic states which are local minima of the energy function of the Hamiltonian. By local minimum, I basically mean that any local change of the variables basically increases the energy. So, I mean, just to give you a concrete example, we again look at this kind of model where the basic variables are just plus or minus, discrete variables, plus minus, and these are called Ising variables. And then there is some interaction which is tells us about how and this sum is over, this Ising variables are sitting at lattice sites, and this sum is over some pairs of lattice sites, and there is some coupling constant Jij, which depends on which particular kind of problem that you're interested in, ferromagnetic or antiferromagnetic, things like that, which will come to later on. But the point is, now given this sigmas, one can of course calculate what the value of the energy is going to be. Now the question is, there are some special states such that if I take that spin configuration and flip meaning, I mean, change the sign of sigma from +1 to -1 or the other way around. If I change, let's say, the kth spin from sigma k to minus sigma k, and if any such change actually increases the energy of the system, then I would call that state a local minimum, or a state which is stable under single spin flips. So here we are talking about not global minimum. Global minimum is where you find the values of the sigmas for which the energy has the smallest possible value. But here, what is not demanding this, one is demanding that if I flip any spin, then the energy will go up. So that particular configuration, that for which this is true, will be called local minimum or single flip stable state. So to see that, this condition that I have just written down here, basically it amounts to the same thing that I have written down over here. Because as you can see here, this Jij and multiplied by sigma j and summing over all j gives you some kind of a local field that is acting at site I. And when the spin at that particular site and the local field, they are pointing in the same direction, then that gives you a negative contribution to the energy. And so whenever this condition is satisfied for all I, we have a situation where one is dealing with a local minimum of the energy. And the reason that in statistical physics one might be interested in, especially looking at such states, is that now we have to go a little bit beyond equilibrium statistical mechanics. We have to look at some kind of dynamics. And this kind of states will play an important role in the dynamics, assuming that the dynamics proceeds via single spin flips. So, and that's not difficult to see. So these microscopic states, which are stable against single spin flip, basically means that every single spin flip will increase the energy of the system. That's how you define it. This is where the dynamics may get stuck. Of course, I mean, this Ising models doesn't have any dynamics on its own. You have to sort of supplement it with some additional dynamics. And a dynamics that is often used to describe this kind of discrete systems is this Metropolis Monte Carlo dynamics. Everybody familiar with it? Metropolis, yeah, I guess. More or less. So I don't have to go into details, but basically this Metropolis dynamics proceeds through, let's say, single spin flips. and a spin flip is accepted or not. That depends on whether that spin flip will increase the energy or decrease the energy. Okay. So basically what one does is just one spin is chosen at random. It's a candidate to flip, and whether you flip it or not, that decision is based on whether this flip is going to increase or decrease the energy. If it is decreasing the energy, then you accept the flip with probability 1. If it is going to increase the energy, then there is this probability with which you accept that move. T going to 0, of course, basically means that for any negative delta E, this probability is going to go to 0. So 0 temperature, Monte Carlo dynamics, basically means that you try to flip the spins at random, and spin flip will be accepted only if by flipping the spin you are going to decrease the energy. Now this kind of single spin flip stable states that I'm talking about are such, by definition, constructed in such a way that if you flip any spin, it will actually increase the energy. So no such flip will be accepted at t equals 0 if this is the dynamics that you are assuming for your system. So this kind of this dynamics, I mean, although I have sort of introduced it in the context of equilibrium statistical mechanics, doesn't have to be like that. I mean, in many other systems that people are interested in the context of statistical physics, similar dynamics is used. And there, although there may not be an energy or anything like that, but one can still think in terms of the dynamical rule will tell you which flips are allowed and which flips are not allowed. And so there will be some such states which are stable in the sense that this kind of moves are not allowed for those states, and those states system will get stuck into those states through its dynamics. Temperature, this is no, so I mean, this is, you have to keep in mind that this comes in here. Here. The absolute temperature that tells you about the probability of the various microscopic states that you have in your system. Combinatorial system, there's no sort of obvious definition of a temperature. But if you are thinking in terms of, let's say, a collection of bistable elements which are connected to each other and they undergo their dynamics and so on and so forth, then this temperature can be thought of as something to do with noise. I mean, if there is no noise in the evolution of the system, then it's somewhat similar to the zero temperature dynamics, that you flip or not flip with just basically deterministically. There is no probability associated with it. Whereas if there is some noise, then at least approximately one can model that by introducing this, for example, in the metropolis dynamics. So here you see that here one actually allows flips which increase the energy, but it occurs with a probability which is related to how much the energy is going to change, and this parameter t. So t going to 0 basically means you don't accept such moves at all. T is very large basically means that you accept such moves with high probability. So, and then if you want to sort of look at a specific model or specific system for which this kind of thing is allowed, then often this temperature is taken to be a measure of some kind of noise in the underlying dynamic. Yes. So that's actually one of the interesting issues. For example, I mean, given a particular model Hamiltonian, one may ask this question of how many such states will be there which will satisfy this stability against single spin flip. One can also inquire about how the energies of those states are distributed. All of them will not have the same energy and so on. So in general, it's not so easy to actually answer questions like that, complicated Hamiltonians. But these are kind of issues that people are concerned about, yes. So basically, dynamics will get stuck, etc., etc. And there, some of you have heard about, I mean, at least in the context of optimization, there was a lot of work on this thing called simulated annealing, which is basically making sure that this, are trying to develop some procedures which prevent the system from getting stuck into this local minima. So at a finite temperature, you can easily see where that comes in, since that when t is finite, not 0, then these moves will actually take place with some probability, which will allow the system sometimes to get out of this local minima and then try to explore the global minima of the system. And this simulated annealing actually was developed by Scott Kirkpatrick and a couple of other people at IBM. And they were actually working on their statistical mechanics people. Kirkpatrick is working on disordered systems and things like that, for which they were trying to find ways of going to low energy states of the system. And this method that was very popular some time ago actually came out of that. Okay, so this is the general introduction. Basically, what is the general problem in StatMech? And a few things that I tried to sort of point out where those things make contact with some problems in computer science or similar problems that we'll be discussing throughout this. There are some specific problems, there are specific questions about these things, then we can try to address them, otherwise we'll go into the next topic, which is, Okay, so this is again something that Partho mentioned. One of the sort of most interesting things that physicists have spent a lot of time in trying to understand are these phase transitions. And I'm just going to spend some 10-15 minutes on telling you about some specific interesting properties of these phase transitions. And again, you know, I'm sure all of you know generally that, you know, there are these transitions from one phase to another. These different phases in general have very different physical properties. And then as you change some external parameter, like either the pressure here or the temperature there, system goes from one phase to another across lines, which are phase boundaries. And drastic change happens as one goes from this side to that side or this side to that side, like that. And thermodynamic quantities that I had defined, for example, the Helmholtz free energy, can be studied as a function of temperature as one goes across one of these phase boundaries. And generally one may find some singularities, or the derivatives of the Helmholtz energy may have some singularities as one crosses such phase boundaries. And depending on that, there is a classification scheme. Again, I don't want to go into this because it's not really very much relevant. But there are phase transitions for which there are discontinuities as one goes across the phase boundary. I mean, if you look at the Helmholtz free energy is always continuous. But if I take a derivative of that with respect to temperature or magnetic field and things like that, then we get this thermodynamic quantities like here, for example, one thing that I did talk about a little bit in detail is the entropy, where you look at the Helmholtz free energy and take a derivative of that with respect to the temperature, gives you the entropy. And there are some phase transitions in which this quantity changes discontinuously. That as one goes from one phase to another across the phase boundary, there is a discontinuous change in the entropy. And again, you know, from your high school physics, probably you remember that this is related to what is known as latent heat and so on and so forth. So there are phase transitions in which this latent heat kind of things are present, and those are called first order. There are other phase transitions where this kind of discontinuity does not happen. The first derivative of the free energy with respect to temperature, magnetic field, etc., also are continuous, but there could be some divergences. Large fluctuations and things like susceptibility, they diverge at as one crosses the phase boundary. And this is known as critical point phenomena, the divergence of these quantities, which basically physically represent large fluctuations near this kind of a phase transition, used to be, or still are, I'm sure, of interest to a lot of physicists. because these divergences turn out to be what is known as universal, in the sense that a very large number of different systems show similar kind of singular behavior as given in terms of exponents of power laws. And the calculation of those exponents from theory is one of the challenges. And I'm sure many of you know that this set of theoretical procedure, renormalization group theory, one of the triumphs of this was basically to be able to calculate what this exponent that tell us about this divergence, or in general non-singular behavior, singular behavior of various quantities at these phase transitions. So this is basically one of the things that I guess will be discussed in some detail here. Partho already had told us about some such systems, about systems in machine learning and other areas of theoretical computer science, where one can actually see examples of such phase transitions, where there could be discontinuities or there could be divergences, powerless singularities, and things like that. There is something here that is actually, I find the most fascinating thing about phase transitions is the spontaneous breaking of symmetry. And I just wanted to mention this because this is one of the examples of something that happens in the limit of large systems, large interacting systems, which doesn't have any analogy with basically what happens when you have a small or finite number of degrees of freedom in your system. In the sense that we have already talked about this energy function of the Hamiltonian. The Hamiltonian has certain symmetries, in the sense that if you, again, examples I'll give just in a second. But it turns out that in many of these phase transitions, the ordered phase, low temperature phase, actually doesn't has the same symmetry as what you have in the Hamiltonian. So some symmetry in the Hamiltonian is spontaneously. Hamiltonian doesn't change, of course. The system is the same particles which are interacting with each other with the same potentials and whatnot. But the thermodynamic state the system is in, that changes in a very dramatic way, such that that thermodynamic state does not breaks one of the symmetries of the underlying Hamiltonian. And this is done, this symmetry breaking happens spontaneously. It's not that one is applying some external field or something like that, which causes this symmetry to be broken. In the thermodynamic limit, one can show, and this is one of the triumphs of, in some sense, well, first, I think, truly established by Onsager for the 2D Ising model, and more recently, of course, I mean, all this RG theory and so on, they also go in the same direction. So this is basically what I'm talking about here. Just look at this kind of a Hamiltonian, that you have this vectors sitting at individual lattice sites, and there's an interaction, which is interaction strength is Jij, depends on the distance between site I and site j. But this dot product, of course, is invariant under simultaneous rotation of the spins. So this Hamiltonian has this property that it is invariant under uniform rotation of the spin vectors. But depending on dimension of physical space and so on, a system described by this Hamiltonian will order. Let's say we are looking at a situation where these j's are all positive, which basically means that these spins want to be parallel to each other. When they're parallel to each other, then the energy is lowered. There is a minus sign somewhere? No, it's not. So then this, whatever, I mean, you see, this j is negative when there is no minus sign here. So point is, I mean, the j's are such that the energy is lowered when all the spins are pointing in the same direction. And that state, of course, breaks this uniform rotation because a particular direction has been picked up. So basically what one has is that at high temperatures, the thermodynamic state of the system basically has the same symmetry as that of the Hamiltonian, which basically means that there is no particular direction in spin space, which is picked up by the system. Whereas as one goes to low temperatures, because of the fact that this energy is lowered, when the spins are pointing in the same direction. Majority of the spins will be pointing in the same direction, and that particular direction being different from all other directions that you have in spin space basically means that one has broken the symmetry, that this rotational symmetry that this Hamiltonian had. And this is done by the system spontaneously. So this spontaneous breaking of symmetry at a phase transition is something that is very sort of interesting and unusual effect. And one in the thermodynamic limit, I mean, one can work out certain models for which one can show this explicitly. Of course, I mean, in experiments, one sees this all the time. Numerical simulations, etc., also will show this breaking of symmetry. Not all of them, no. So, I mean, just let me just. So this is just essentially the same. Since we're talking about this Ising model, let's just instead of vectors, I talk about these things which point up and down, plus or minus. So, and again, you know, here this interaction is such that the sigmas, if they have the same sign, then the energy is lowered. So, and then the ordered state is given by a situation where the average value of this is non-zero, but it is not plus 1 or minus 1. It's that, you know, in the high temperature phase, a particular spin is equally likely to be plus 1 or minus 1, so its average value will be equal to 0. This m will be equal to 0. This is called the order parameter. As you go to a temperature which is lower than a characteristic temperature, then this quantity will begin to have non-zero values. So just look at this picture. So this is in 2 dimensions. Actually, this is just mentioned that this Onsager was the person who actually showed in a highly non-trivial model that this can actually happen. And as you can see here, this is the order parameter, magnetization. High temperatures, it is strictly equal to 0. And as one goes to a characteristic temperature below that, then it begins to rise, but it rises from 0 continuously. So it is an example of what we called a continuous phase transition, where there was no jump, discontinuous jump from 0 to a finite value. Only at 0 absolute temperature, this will be equal to 1, which basically means that all the spins are pointing either in the plus 1 or in the minus 1 direction. So, and as these are examples of this strong fluctuations and the corresponding singular behavior of various thermodynamic quantities, which for this particular model in 2 dimensions can be calculated exactly. And there's a logarithmic singularity, logarithmic divergence of the heat capacity at the point where this happens. But the important thing is that in the ferromagnetic state, majority of the spins will be pointing in the same direction. Paramagnetic state, half of them will be pointing in one direction, half of them will be pointing in the other direction. So the paramagnetic state preserves the symmetry of the Hamiltonian. It doesn't distinguish between up or down, whereas the ferromagnetic state does, in the sense that the system picks up a state where nearly all the spins are pointing in the same direction. And important thing to realize is that there are these 2 sectors. This is again something that will be, I guess, that shows up in many of these problems where you're doing optimization and there are various sectors which have, in some sense, certain properties which are different as one goes from one sector to another. Here, because of the symmetry of the Hamiltonian, this and that, these two have the same energy. But in the, if I look at this probability distribution function, this will not be, will not have the same symmetry at temperatures which are lower than this critical temperature. So that is why the up-down symmetry of the phase is spontaneously broken. That's why you say. Okay. What we have here, let's not worry about it. So the basic physics is simple. It's again this order disorder, in the sense that high temperatures, the spins were pointing up and down with sort of equal probability. Yes. Yes. So that is why, that is the surprising thing, that in the thermodynamic limit, although there are different ordered states related to each other by symmetry. So the Hamiltonian is a symmetry, up-down symmetry, these two states will have the same energy. So if I now look at the Boltzmann weight, exponential minus energy divided by kVt, that also would be the same in the two cases. But when the system goes into a sector where majority of the spins are pointing in one particular direction, then through its time evolution, it cannot go to the other state, and that is possible only when the number of spins is very large. If the number of spins is finite, then these two states will be connected. Given enough time, the system will fluctuate from this to that, and one would see plus or minus equally, and m will be equal to 0. But so this is something that actually I had here. Is just wanted to. So I mean, here let's say this is up sector. This is. So you are looking at a system where you start with all the spins in the up sector, basically, at low temperatures. Then if I want to, and these are denoted by red. If I want to go from red to green, then green is their majority preferentially down. Then to go from here to there has to be some kind of a domain wall, which will separate these two. And the energy to create a domain wall that would diverge in the thermodynamic limit. So it's basically the system chooses to be either in this sector or in that sector. It doesn't, once it has made that choice, then it doesn't see the other sector at all. So very, very crudely speaking, I mean, if I want to have a theory of this phase transition, then the couple of things that one generally takes into account. Again, as I said, there is this Helmholtz free energy, which is energy minus absolute temperature multiplied by the entropy. And one of the principles of thermodynamics is that under the appropriate circumstances, the equilibrium state actually will minimize this free energy. I'm sorry? This one, huh? This is basically, you have to go back to the foundations of statistical physics. For example, I mean, this statement that isolated system always increases the entropy. Given that, one can, so that is like a what is it called, stability or extremization condition that thermodynamic quantity is satisfied. Now, when we talk about this canonical ensemble, we are not talking about isolated system. We are talking about a system which can exchange energy with a heat bath. But you can start with this principle of extremization of the entropy and work out what is the thermodynamic quantity which will be extremized under these circumstances where system is allowed to exchange energy with a heat bath. And there, it's this combination that turns out to be the one that plays the entropy in the case of an isolated system. So here you can see that if you want to minimize this, of course, I mean, this E needs to be, I mean, one requirement is that this E, one way of doing that is to making this E smaller and smaller, or this S bigger and bigger. And the relative importance of these two things depend on this temperature T. When the temperature is large, this entropic part plays an important role, the more dominant role, and the free energy is minimized by basically maximizing the entropy, which is basically the state which is the most disordered, the paramagnetic state in the case of Ising model and things like that. There, the entropy will be large. And so at high temperatures, minimization of this F basically corresponds to, not exactly the same, but it's similar to maximizing the entropy. Yes, the ensemble that I'm talking about, where your physical system is in contact with what is known as a heat bath. And the heat bath has a fixed temperature. And these two can exchange energy. So the system temperature is the same as that of the heat bath. Whereas when this temperature becomes small, importance of this entropy becomes somewhat less. And then one wants to minimize this energy. And energy minimization typically involves going to a more ordered state, whereas maximization of the entropy corresponds to going to a more disordered state. So, and the relative importance of these two are controlled by this temperature. So as you go to lower temperatures, eventually the system can, depends on dimensionality, interactions, and many other things. It can go from disordered state with high entropy to ordered state with low entropy but low energy. So this is basically the general sort of physical way of looking at phase transitions or order disordered transition from a high temperature disordered state to a low temperature more ordered state. Okay, so this is pretty much, yeah. So 2 to 3:30, right? This is what this lecture is going to be for 90 minutes. So this is a general description of phase transitions. Are there any specific questions about these things? Okay, so then, yeah, sure. So I mean that comes in. See, let's say in StatMech, often we are given a model, and we want to find out, for example, what kind of phases it will exhibit and what kind of transitions and so on. And exact solution is very difficult or not possible in most cases. So we have to do some things like this Monte Carlo, for example. Monte Carlo, by definition, is basically some kind of a dynamics, some way of going from one configuration to the next one, etc. There, as Partho was saying, depending on the dynamics that is being used, the probability of the system getting stuck into this kind of metastable states and on, those things will come into the picture. And a lot of effort actually goes into the development of algorithms which will avoid, to some extent, this possibility of getting stuck in shallow minima and stuff like that. So although the actual dynamics of the system is not, in many cases, is not really related to that you are simulating the system on the computer. On the computer, you are interested in equilibrium behavior, let's say, and you want to generate a set of configurations which are distributed according to the Boltzmann distribution. And you want to do it in a somewhat efficient way. And so people come up with cluster moves, and then they have these reweighting techniques and so on and so forth. Many different ways which are artificial, but which are guaranteed to generate the Boltzmann distribution without getting stuck into some of these metastability issues and things like that. So that actually is a sort of fairly important line of research for people who do these Monte Carlo simulations to study various phase transitions and stuff like that. Then there are, of course, issues related to dynamics itself, which I'm not going to discuss here. The dynamics have to be, in some sense, chosen in such a way that it has some physical basis. That this is how actually the variables that you have in your system are going to evolve in time. And there, at low temperatures, one has to worry about quantum mechanics and stuff like that. So it becomes more complicated. But these are all sort of questions that keep a lot of people busy. Right. So that was coming to at the end, a little bit of that. Yeah. Right. Yes. So overall average, you have to then again, think about what is it that you're trying to describe. So the claim is that, let's say I start with this system at high temperatures. I cool the system down. There will be a characteristic temperature, which is the temperature of the phase transition, in which the system would either go into the plus M sector or minus M sector. It will, once it has gone into the plus M sector, then you can wait for a very long time, observe the system for a very long time, but it will not fluctuate into the minus m sector. So when you actually calculate, the thing that we'll see, either in a simulation or in a real experiment, is that one or the other. Both of them are equally likely. So the fact that the Hamiltonian has this up-down symmetry basically means that there is no bias as to whether it will go into the plus m sector or the minus m sector. Which one the system will choose will depend on fluctuations, ambient fluctuations and things like that. Right. So P sigma, let's say sigma I correspond to this configuration. So system, once the system has gone into this sector where this is close to 1, has a large value, then during its time evolution, it will not see that one. Although mathematically, if I look at the actual formula for sigma I, then this should be the same. So this is basically, there's this famous statement which is attributed to P.W. Anderson, who is one of our condensed matter physics, is probably one of the most famous physicists. There's a slogan which is called "More is different." So the claim is that as you go to very large systems, interacting systems, then they exhibit properties which are sort of counterintuitive, which just by looking at Hamiltonian or the specification of the system, you would not be able to guess beforehand that this is going to happen, and new things emerge as a sort of collective behavior of the system. And this spontaneous symmetry breaking is, I find, one of the most surprising things that actually emerge because of the presence of a very large number of particles. Okay, so I have told you about some characteristics of these phase transitions. The question is, what do we do theoretically? How do we actually analyze these phase transitions and try to find out, for example, at what temperature it will occur, how the various thermodynamic quantities will behave as one crosses this phase boundary and so on. And the exact solutions are very rare. Two-dimensional problems, Ising model, the Onsager solution is there. There are a few other models, Baxter model and things like that, for which exact solutions are there. But it's 3 dimensions, hardly any non-trivial model actually has the exact solution. And so one has to develop some kind of approximate methods. And this midfield theory is something that at least, for many, you have, Z or F, I mean the free energy, has a closed form expression in terms of the variables of the problem. The variables of this problem here, for example, that would be the number of spins, n, the temperature, there could be an external magnetic field, things like that. So this Millfield theory is a sort of simple way of seeing, in some sense, get some physical feel of why this kind of phase transitions occur, and at least in some cases this also is exact, and many of the things that we'll talk about, that we'll hear about tomorrow, will be basically based on Millfield theory. So I just wanted to spend maybe 10 minutes on, and this is one of the first things, one of the simplest theory of phase transition, so to speak, and it gives you some physical idea as to why these phase transitions occur. So this is, there are a couple of slides where I have a little bit of algebra. Again, same model is being looked at, sigma I, sigma j, and let's say it's nearest neighbor interactions. Order parameter is the average value of these spins. And one way of looking at Millfield theory, Millfield theory comes also in many different versions, and there are different ways of sort of justifying that particular version of Millfield theory. But here I'll be looking at it as a theoretical description, which is simple because it reduces the problem to individual variables. I mean, the whole problem is difficult because all these sigmas are coupled with each other. A particular sigma is coupled to its neighbors. they themselves are coupled to their neighbors and so on and so forth. This coupling is what is difficult to take into account theoretically. But if there is some way of sort of reducing this problem to a single spin problem, then of course everybody knows how to handle it, because one can always handle one spin at a time. And here I've just sketched a way of doing that, which is basically writing this sigma I, sigma j, this is a coupling term, in terms of average value and fluctuation. And then when you expand this thing out, this correlation of fluctuations you ignore. Delta sigma I is the fluctuation of the ith spin, delta sigma j is the fluctuation of the jth spin, and there is of course a term which is a product of these two. But just to reduce this problem to a single spin problem, effective single spin problem, you neglect that term, and then it's very simple to do a little bit of algebra to write this Hamiltonian in min field approximation as one involving just single spin terms. And here the single spin term comes with this m, which is unknown of course, and which is the order parameter that we want to calculate. So given this, then one can of course do the standard thing of calculating sigma average using this single spin Hamiltonian, and one gets a self-consistency condition for this order parameter m. And here beta is 1 over temperature, J is the coupling constant, Z is the number of nearest neighbors. The spins are sitting on a lattice, so you have some number of nearest neighbors. And as you can see here, here m equals 0 is always a solution. That's the paramagnetic solution, disordered state. But as one increases this beta, then below a certain temperature, temperature is given by this quantity, there is an non-trivial solution, and that basically tells you that as you go below that temperature, the value of m begins to pick up from 0, and that is the continuous phase transition that we were talking about. So as you can see here, it's certainly not an exact solution. I mean, it's just throwing out a large part of the problem by saying that fluctuation of the ith spin and the fluctuation of the jth spin, product of this, that is ignored, and as a result, one basically reduces the interacting problem to a non-interacting problem, but it has to be solved self-consistently because the parameter that goes into this non-interacting approximation itself is not known, and one has to do this self-consistently. So, as you can see here, m equals 0 is definitely a solution. The question is, I mean, the phase transition here would correspond to going from m equals 0 to a non-zero value of m. So, whether this equation will admit a solution which is non-zero value of m, and then one has to look at the free energy of this solution and the solution with m equals 0 and see which one has the lower free energy. So, actually, this is a simple picture that tells you that. There is a graphical solution, and when the slope of this is the hyperbolic tangent, when the slope becomes bigger than 1 at the origin, then at that point one has a non-zero solution, and one can show that that solution actually has a lower free energy as compared to the other one. What do you... Mm-hmm. That's not true, yes. So, I mean, this is an approximation. This is actually not a good approximation. If I look at the result of this TC, for example, that will turn out to be quite different from the actual TC that the system has. So it is it's neglecting a lot of physics. And just one thing I want to show is that in certain limits, this becomes exact. For a physical system with short-range interactions in 2 dimensions, 3 dimensions, this approximation, although it gives you something that looks reasonable, it is not quantitatively correct. No. So, I mean, in the previous thing, what I say, one way of looking at this is that, you see, each spin sigma I is interacting with some of its neighbors. Z is the number of such neighbors. And here what one is assuming is that all the other, let's say I'm looking at a particular I, all the J's replace them by their average values. Right? So there are Z such quantities. M is the average. And so this is why it is called mean field, that all the neighbors are assumed to have the average value of the sigmas. That sigma I is sitting there, and then you have basically J times Z times I. Yeah, so this gives you, I mean, a phase transition, and one can calculate various singular behavior at the phase transition and so on. But these are not the right behavior in the sense that if you, two-dimensional, for example, there is an exact solution. And the singularities that you get in the exact solution will be different from the singularities that this mean field kind of a treatment will show. But there is, and this is, I think, many of the spin glass models and many of the optimization models also are fall under this, where the system is such that every spin interacts with every other spin. So, I mean, what we were talking about earlier is that a particular spin has some 6 neighbors or 4 neighbors or whatever, and the interaction doesn't go beyond that. But now one can construct models where every spin interacts with every other spin. And for such models, one can show, and it's a fairly easy few lines of algebra to show, that this mean field approximation becomes exact. So there will be spin glass models with infinite range interaction. There will be other models. I mean, here one can, this is the ferromagnetic model, where the sigma I, sigma j, there is a coupling constant j, which is positive, and every pair, the interaction is there. And this model can be, the thermodynamics of this model can be worked out explicitly, actually quite simple. And one gets results which are basically the same as what this mean field theory would predict. And the way I do it is, I don't want to go into all this algebra, but the advantage of this infinite range interaction is that if I say that so many of them are up and so many of them are down, both the energy and the entropy can be calculated exactly. Because in other cases you cannot say. If you have just nearest neighbor interactions and you say that half of the spins are up, that doesn't mean, that doesn't tell me what the energy of that state is going to be, because it depends on how you arrange the up and down spins on the lattice. Whereas if everything interacts with everything else, then it doesn't matter exactly where they are sitting. So as soon as you fix how many spins are up and how many spins are down, then you can calculate the internal energy explicitly. You can calculate the number of microstates with magnetization M, and you can calculate the corresponding entropy explicitly. And then the free energy has now exact expression in terms of this order parameter. And you minimize this with respect to M, and you get back exactly the mean field approximation for the magnetization. And if you look at this free energy, then it has this structure that at high temperatures, it has only one minimum at M equals 0. As one goes to lower temperatures, one begins to see the development of other minimum, and system going from this M equals 0 minimum to that is basically the ferromagnetic transition. And as you can see, because the symmetry, as soon as you have a positive M minimum, you will also have a negative M minimum, which is degenerate with the positive M minimum. Okay, so this is sort of the simplest level theory of a phase transition, which shows non-trivial behavior as a function of temperature. Yes? Okay, so I have 15 minutes and more or less on time. So if there are no questions about this, then we'll go on to the brief introduction to disordered systems, which, as we'll see, will be taken up in much more detail tomorrow. And we'll see, I mean, that's where actually many of the analogies of this phase transitions here and in computer science and things like that, they come into the picture. Yes. 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 So one can look at models where the interaction between two pairs, two spins in a pair, falls off, let's say, as some power law of the distance between these two sides. And then there is an exponent that associated with that power law. And if that power law exponent, depending on the value of that power law, mean field theory may or may not be exact. If it falls off sufficiently slowly, then mean field theory becomes okay. So far I have been talking about systems which, I mean, all the Hamiltonians that I wrote down, etc., etc. There was no distinction between whether you are looking at this part of the system or that part of the system. I mean, you put the spins on a lattice and you look at a nearest neighbor pair anywhere in the lattice, the interaction is the same. So there, those systems are called non-disordered or translationally invariant models, where the interaction parameters do not vary as you go from one part of the lattice to some other part of the lattice. They're the same everywhere. But there are systems, and of course, in physics there are many such systems, where different parts of the system, the parameters that appear there, are actually not quite the same. That a bond could have a value plus 5, some other bond which is sort of looks the same as that in the sense that the nearest neighbor bond, but it could have a value of -5 or -10 or whatever. So I mean, system is not translationally invariant, and simple example of this is something that I'm sure all of you can imagine. It's basically, let's say, I have a magnetic system. There at lattice sites, you have these spins sitting there, and they interact and they can order and so on and so forth. But I can sort of dilute the system by replacing some of this magnetic species by some neutral species, which doesn't have any spins associated with it. So then there will be some sites of the lattice where there are vacancies, there are no magnetic spins, some other sites where the magnetic spins are sitting. And if I want to write down the Hamiltonian, I'll write it down like this. That sigma I, sigma j are the old variables, Ising variables that I had talked about earlier. But now, in addition to that, I'm introducing these occupation variables, Ni and j. Ni plus 1 corresponds to site I being occupied by a magnetic species, and 0 corresponds to site I being, so this should be unoccupied. This cut and paste problem. And these are the variables. If you have a solid state sample, then certain sites are not occupied, and this thing doesn't change as a function of time. Whereas the spins can flip. So now we have two kinds of variables. One is basically the dynamical variables, the spin variables, which can flip, change its state from +1 to -1 and things like that. But there is other set of variables which do not change as a function of time. Certain sites are selected for which these Ni's are 1, and some other sites the Ni's are equal to 0. The number of such sites for which it is 0 or 1, that will depend on the concentration of the impurities or the non-magnetic species that you have in your system. So this is what we specify. We don't specify this site is occupied, that site is occupied, and so on and so forth. We say that a fraction C concentration of the impurities is there. So, and these impurity sites are chosen at random, and different samples will have different positions of these impurity sites. And these two will not match in general, but statistically they will be similar in the sense that the same C will be there. The fraction of impurity sites in two such samples will be the same, but their actual locations will not be the same. And once in a particular system, we have chosen the location of this Ni equals 1 and Ni equals 0. This doesn't change as a function of time. And this is why these variables are called quenched, that they're not dynamical variables. They do not have any change as a function of time. So there are now many such, a very large number of such systems, disordered systems that people are interested in. And there are phase transitions and all sorts of interesting things going on. So let's see how much. One such example is what is known as spin glasses, and we'll hear more about spin glass models later on. is, again, solid state physics you don't have to really worry about. But the point is, now there are these lattice sites where whenever I put an arrow here, it basically means that a spin is sitting there. A vector variable is sitting there. And the interaction between a pair that has this oscillatory form. So this interaction can be either positive or negative. So we basically have a situation where there are these randomly located sites, and the interactions between pairs of this can be either positive or negative, depending on where they are located. And as a result, one has strange magnetic behavior of this materials. And this is the important slide that we'll be referring to perhaps later also in this workshop. Here, just as I was saying that here, because of the oscillatory nature of this function, depending on the value of r, some interactions could be positive and some interactions could be negative sign. So just take, let's say, a triangle like that. And let's say all these three interactions are negative. Then you can easily see that it is not possible to find a spin configuration for which all these three bonds are happy, in the sense that we cannot minimize the energy associated with a particular bond, cannot do that simultaneously for all these three different bonds that you have here, because let's say you start with this, and let's say this is +1. Then since this interaction is negative, this would like to be -1. This interaction is negative, this would like to be +1. But then you would have these two +1s which are connected by an antiferromagnetic bond, and so the energy associated with this antiferromagnetic bond is no longer minimized. And when you have this sort of mixture of positive and negative and so on and so forth, or you can have an external magnetic field which sort of competes with the exchange interactions and so on and so forth, you have what is known as frustration. And which basically means that if I now look at all the pair interactions, you cannot minimize the energy associated with all of them by a particular spin configuration. And so that's something that you have shown here. And this is an important aspect of many random systems. And those random systems will exhibit, because of the sort of basic nature of this frustration phenomenon, will exhibit multiplicity of ground states. And the way to see that, I mean, in a very simple way, is that here, if you have a situation like this is a frustrated plaquette, the choice of the bond which is not satisfied can be either here, here, or there. So even here, just for when you have just three such spins, it is possible to have three different configurations of the spins for which the energy is minimized. And if you go on a much bigger lattice and put in many such spins and so on, it is not difficult to see that it will lead to a multiplicity of ground states and metastable states, basically. And this is what makes the problem in some sense highly non-trivial. In the sense that given, let's see, what do we have in the next? Yeah, so this is a model. I'll just stop. This is the last but one transparency, I think. So this spin glass we just mentioned, and a model that has been studied a lot in that context is basically this model which was written down by Edwards and Anderson, many years ago. So again, the form of the Hamiltonian is the same, the Ising model. So sigma I can be, each variable can be ±1. The point is, these Jijs now are random variables. We are now talking about disordered systems. So going back to the picture where you have the spin sitting and they had different interactions depending on the distance between them. So here we are doing the same thing, except that we are saying now that the spins are sitting on a regular lattice and we are making these Jijs random variables, and they are taken from a particular distribution, which of course depends on the model that you want to study. So here, each Jij is an independent random variable. The joint probability is basically a product measure. And one basically, again, the actual form of this probability distribution, the people have chosen different models to study. Simplest one is where you have a Gaussian distribution centered at 0. So there are both positive and negative bonds which are equally likely, which sort of crudely means that both ferro and antiferromagnetism are equally likely. So this model cannot have the usual conventional kind of magnetic order, but then depending on dimension and things like that, it can actually exhibit some kind of a phase transition from a high temperature disordered state to a low temperature ordered state. But this ordered state is quite different from ordinary ferro or antiferromagnet in the sense that they don't have this kind of long range order, but the kind of long range order they have is this. High temperature phase, the spin averages are equal to 0. So that's the paramagnetic phase. It's not anything different from the paramagnetic phase that you see in other magnetic systems. There are differences, but not very sort of strongly different. Here, the low temperature phase is very different. The low temperature phase has this thermal averages to be non-zero. So the spins are frozen. But the spins are frozen in, some of them are in the up direction, some of them are in the down direction. And so there is no net magnetization. Equal number of spins are frozen in the +1 direction as compared to the -1 direction. And so the conventional magnetization order parameter that one uses to describe ferromagnetism is not appropriate here, that is 0. But there is a new order parameter that was developed by Edwards and Anderson, which now expresses the fact that these thermal averages themselves are not equal to 0. So, and that is a simple way of doing that is basically take the thermal average squared and then average it over all the spins, and then you would get a non-zero value. And that would be the spin glass phase where the spins are frozen, and it's different from the high temperature paramagnetic phase in the sense that this order parameter will be 0 in the high temperature phase. So as you can see here, because of the disorder, some new kind of phase is now possible. And this is where, this, as you can see here, this is in the early 70s. People started, many statistical physics people started thinking about how to describe this kind of system. Various mathematical methods were developed. One of them is the replica method, which you will hear about more in the, tomorrow's morning tutorial session. And then many new things also came about. That the low temperature phase here, of course, the order parameter is different from anything that you have seen earlier. And now if I look at another thing that people found is that because of the presence of disorder, frustration, and a large number of local and minima of the free energy, this low temperature phase exhibits many properties which are also quite unusual. And if you have this many minima, then they will be separated by potential energy barriers. And so the system to explore the whole of phase space will be very difficult. Dynamics becomes very slow. So there are things called aging and various other physical quantities that one can observe in experiments, which basically are manifestations of this slow dynamics. And so this is where this glass name comes into the picture. The glass is typically something that evolves very slowly in time and takes a very long time to equilibrate, is generally called a glass, and also something which is disordered. So these are all such examples. Spin glass is perhaps one of the sort of most extensively studied such disordered system. And this presence of multiple minima and the complex dynamics that is associated with the presence of such multiple minima, these will also have counterparts in some of these optimization problems or other problems which are relevant to the theme of this meeting. So we'll hear, I'm sure, more about it. Let's see, did I have other things? No, I think just one more slide I want to show, which will lead into, I think, tomorrow's talk in a reasonable way. This model that people looked at, this is called the Sherrington-Kirkpatrick model, is an infinite range model. And I mentioned this because in the context of mean field theory, I had told you that infinite range models, the mean field theory becomes exact. So here also, there is a mean field theory for this infinite range spin glass model, which was worked out by Thouless-Anderson-Palmer. And one can explicitly write down the free energy in terms of this order parameters. Now, there is a big difference between this and the ferromagnet, because in the ferromagnet, the order parameter was a global order, in the sense that all the spins, it was a translationally invariant system. So if I look at the sigma I average, it doesn't depend on I anymore. Sigma I average is the same for all I. So there's only one order parameter, M. But now we are talking about it is disordered system, which does not have a translational invariance. So for a particular system, which is given by a particular choice realization of this Jijs, in general, the M's will vary from one site to another. And one can write down the free energy explicitly in terms of this M's. There is a term which is called, there's a new term. I mean, you see, if you look at this term, this was there in Jm squared term in the ferromagnet. This term, entropy term, also was the same as that. But there is now a new term which is called the Onsager reaction term, which comes from the fact that you have basically, if I look at two spins I and j, and look at the influence of j on I, we have to subtract from the magnetization of j the influence of I itself. In the sense that we shouldn't double count. That here, mj, site j is being actually affecting site I, but part of mj actually is coming from the influence on site j coming from site I. And that part has to be subtracted out, and this is this reaction term. And so once one takes that into account, this is now exact for this infinite range spin glass. And one can see all this multiplicity of solutions, etc., which are sort of hallmarks of a disordered system. In this case, just by looking at this TAP equation and looking at its minima, local minima and global minima, as a function of all the M's. And this gives you this complex free energy landscape, slow dynamics, etc., which we'll discuss in more detail as we proceed through these next few days. Okay, so I think this is a good place to stop. Yeah. Previous slide, yes. You cannot see there are a few things that one can do analytically. For example, if I want to look stationary points of this free energy, then I can estimate that. But specific, I mean, given a particular Jijs, unless you have a big computer, I mean, you cannot do very much analytically. Very close to the transition temperature, where all these M's are going to be small, there again one can do a few things analytically.
But qualitatively, do you see anything from these equations, or what?
Yeah, so that is a few things. I mean, just by looking at this small m, one can estimate what the transition temperature is going to be. One can look at, let's say, the m equals 0 solution. That's always there. All the m's equal to 0. And one can basically look at, let's say, small fluctuations about the m equals 0 solution. One can get a quadratic form, one can get a susceptibility, and one can then try to find out when the susceptibility becomes divergent. That will give you the analytic result for the transition temperature. High temperature phase and up to the transition temperature, one can do analytically. Below, because of the fact that now there are this multiple minima and this number of minima is actually exponentially large, there doing something analytically is difficult.
Is it assumed that the Jij are measured and you know what they are?
Jij is this problem specification. What one specifies is the probability associated with having a particular set of Jijs.
Okay.
And generally one assumes that these are independent random variables. So one just assumes some kind of a Gaussian or double. So I mean,
the reason I ask is the specific MI will depend on the realization of the JIJs.
Right. So that's the that's why this is interesting in the sense that here I have all the JIJs are there. So you have a particular sample. Particular sample basically, or realization of the disorder. That basically means that all the pairs here, let's say we are doing infinite range interactions. So for every pair, for every sigma I and sigma j, there is a Jij associated with it. And that Jij value is to be taken from a distribution.
So one looks at an ensemble of J's and then study.
Right, but for a particular sample, you have chosen that particular value of J's. And for that particular sample, the values of this M's, etc., will depend on that particular choice.
Correct, yes.
Yeah.
Would it be correct to say that when you have multiple phases in the infinite limit, for the corresponding dynamics, the quasi-invariant sets split into separate ergodic sets?
Yes, I mean, that depends on which model you are talking about. For the Edwards-Anderson model, where all the interactions are short range, there, how many ergodic sets are there? There's a huge controversy about that. For the Schrenk-Kirkpatrick model, the one where you have min-field infinite range interactions, there the barriers, when there are these separate sectors associated with minima of the TAP equation, free energy, or the corresponding Hamiltonian, and there the barriers do diverge. So in the thermodynamic limit, in the low temperature phase, the phase space gets broken up into sectors. But in the short range case, it's a 30-year controversy as to whether there are just two, there is, of course, for every sigma state, there will be a minus sigma state. The question is, these two are always ergodically separated. The question is, these are the only two sectors, or each of these also are further broken up into smaller sectors?